Taylor theorem. If f and its first nth derivative are continuous on the closed interval between a and b, and the nth derivative is differentiable on an open interval between a and b, then there exists a number c between a and b such that f of b equal f of a plus f prime of a times b minus a plus f double prime of a divided by 2 factorial times b minus a square plus so on and so forth. Now, in the Taylor formulas, if f had derivative of all order in an open interval I contained in A, then for each positive integer n and for each x in I, we can have that polynomial that you can see there. Now, in approximation, using Taylor's theory to approximate a graph, the real question is that how many terms of the Taylor theory do you really need to use in order to get a very good approximation of the graph? Well, in a sense, in this case, we're saying that we can use up to polynomials piece of n to approximate the graph of f of x, and we left over with the last term. These are the leftover, and we call them the remainder. Okay, call the remainder of the order n for the error term. That's the error of approximation. So if r sub n go to 0 and n go to infinity for all x in I, we say that the Taylor series generated by f at x equal a convert to f. So the Taylor series actually convert to the function on the interval I, and we write f of x equal the sum from k equals 0 to infinity of the k derivative of a divided by k factorial times x minus a to the k. Let's see how that works in an example. Show that the Taylor series generated by f of x equal x squared at x equals 0 convert to f of x for every real value of x. So first of all, this function have derivative in all order, and we know derivative of e to the x is e to the x. Okay, so we can write down e to the x is equal to 1 plus x squared divided by 2 factorial plus so on and so forth, x sub n divided by n factorial plus the remainder term. Okay. And here we know that r sub n is equal to e to the a, e to the c divided by n plus 1 factorial times x to the n plus 1. Okay. For some c between 0 and x. Now, since e of x is an increasing function of f of x, e to the c lie between e to the 0 and e to the x. So when x is negative, so is c. That's the case, e to the c is less than 1. When x equal to 0, e to the x equal 1. So here, r sub n of x is equal to 0 when x is positive. and here's e to the c will be less than e to the x. So let's take a look at absolute value of r sub n x. This has to be less than or equal to absolute value of x to the n plus 1 divided by n plus 1 factorial when x is less than or equal to 0. Okay, an absolute value of Rn of x is less than e to the x times x to the n plus 1 divided by n plus 1 factorial when x is greater than 0. So here, little note, this happened because when e to the c less than 1, since c is less than 0, if that's the case, e to the c is less than e to the x. Since c is less than x, right? And because the limit at n approaches infinity of x to the n plus 1 divided by n plus 1 factorial is equal to 0 for all x. This meant that the series converged to e to the x for every x. For all x. Let's talk about the remainder theorem. If there is a positive constant capital M such that the n plus 1 derivative of t is less than or equal to m for all t between x and a inclusive, then the remainder term R sub n in Taylor theorem satisfies this inequality. If this inequality holds for every n and other conditions of Taylor theorem are satisfied by f, then the series converges to f of x. Let's show that the Taylor series for psi of x at x equals 0 converges for all x. So you do the work and you can see that the Taylor series for psi of x is equal to x minus x to the third divided by 3 factorial plus x to the fifth divided by 5 factorial, so on and so forth, plus negative 1 to the k times x to the 2k plus 1 divided by 2k plus 1 factorial plus the remainder 2k plus 1 of x. Well, because we have a psi function, all the derivative of psi of x have absolute value less than or equal to 1. So then we can apply the remainder, estimate remainder theorem with m equal 1. So then now I have absolute value of 2k plus 1 x less than equal 1 times absolute value of x to the 2k plus 1 divided by 2k plus 1 factorial, 2k plus 2 factorial. Well, the limit at k go to infinity of 1 of the absolute value of x to the 2k plus 1 divided by 2k plus 2 factorial, this equal to 0. So then this implies side of x converge. The Taylor series of side of x convert to side of x for all x. So for what value of x can we replace side of x by x minus x to the third divided by 3 factorial and obtain the error whose the magnitude is no greater than 3 times 10 to the negative 4? Well, let's go ahead and write out a couple terms of the Taylor series for side of x. Side of x equal x minus x to the third divided by 3 factorial plus x to the fifth divided by 5 factorial plus x to the 7 divided by 7 factorial, and we have alternating signs, so this should be negative, so on and so forth. Well, let's take a look at this. If I write this down, this is x minus x to the third times 3 factorial plus x to the fifth 5 factorial equal to 120 minus x to the 7 and 7 factorial equal 5040. Okay. So note that after this term, x minus x to the third to 3 factorial, every term after this is no greater than x to the fifth divided by 120. Okay. So let's see. Let's just try to solve that inequality. We want the magnitude is no greater than this, then the absolute value of x to the fifth divided by 120 have to be less than 3 times 10 to the negative 4. We solve this inequality, we will see that the absolute value of x is about 0.514. Okay. So that's what we can replace x by.